Okay, this optimization problem, I think many of my students historically have found challenging. It's a multiple choice. It's from Khan Academy. It says, in a restaurant, the daily menu is mounted on a wallboard. The printed region with today's entrees include 216 square inches of text. If there are 2-inch margins on the sides and 3-inch margins at the bottom and the top, what are the dimensions of the smallest piece of wallboard that can be used for the menu? All right, so your wallboard's looking like this. Let me just try to sketch it. So like there's our wallboard. And what they're saying is there's going to be some writing in the middle. So I'm going to just kind of draw an interior part. Almost like a picture frame here. And like this all needs to be print. Right, writing's going to be there. It says there are 2-inch margins on the sides, so I'll just indicate that. 2. Okay, 2-inch margins on the sides, and 3-inch margins at the bottom and the top. And then it says, what are the dimensions of the smallest piece of wallboard that can be used for the menu? So then the constraint too is at the print area, right? 216 square inches of text is the printed region. So this area in here equals 216 square inches. Okay, so what do we need? We need a model for to represent the area of this wallboard. So the smallest piece of wallboard implies that you're minimizing area. So I got to introduce some variables, and there's, you could let your variables be the interior, the like internal rectangle or the external. I'm gonna call, since I'm trying to find the basically the dimensions of the wallboard, I'm gonna start by labeling those variables. So I'll call that y, and the height here. Right, so that's x. I'm gonna call the height here y. Okay, so let's start working on our model. Okay, so my model is like I want to minimize the area. So I'll say A equals, well, the area of my wallboard is x times y. Now I got a constraint. The constraint is that this area in the inside has to be 216 square inches. So my constraint is that that area has to be 216. So like let's start working on expressions. Like what is the area of this rectangle as an expression? Well, that must be x minus 4, right? If you take off the two sides. And then this vertical, right? The vertical side must be y minus 6. And so my constraint is that, length times width has to be 216. So I have that x minus 4 times y minus 6 has to equal 216. Okay, so I would love to replace my y coordinate above here as an expression involving x. And I can do that. I'm going to divide both sides by x minus 4. So y minus 6 equals 216 divided by x minus 4. And then I'll just add 6. And that is what I need. So I'm going to bring this up there to get my model. So I think what I'll do, I need more space, but I guess I'll get my model going, and then, so now I can say a of x is equal to x times 216 divided by x minus 4 plus a 6. So there's my model. We might start thinking of a domain. Well, obviously x needs to be positive, But x also has to be greater than 4, right? Because if it was less than 4, you'd have a print area that would have a negative side. So let's just start with that. I need x to be bigger than 4. Okay, so I don't need to consider 4 if it shows up as a critical point or anything like that. All right, so now let's perform some calculus. I'm going to reestablish my model down here. So again, calculus. So I've got a of x is equal to x times 216 over x minus 4 plus 6. All right, and so let's kind of prep this for some calculus. I think I'm going to distribute the x to rewrite it as 216 x over x minus 4 plus 6x. All right, I got to take the derivative. I got to use I think I'm going to use the quotient rule here for that left expression, but hopefully it becomes more manageable. So the quotient rule would say the denominator is x minus 4 squared, and then I have an x minus 4 here. Derivative of the top is 216 minus 216x times the derivative of the bottom, which is 1. And then don't forget the derivative of 6x over there is just 6. So we clean this up, and I get 216x minus 216 times 4 is 864 minus 216x. Okay. So there's my derivative. I can clean it up, but let's just examine whether there's critical points right now. So a critical point will be the derivative is 0 or undefined. Let's check undefined. At x equals 4, the derivative is undefined, but I've already excluded that, right, in my domain, so I don't need to worry about it. The other place is where the derivative is 0. So I'm going to set this equal to 0 while cleaning up. I note that these cancel out, leaving me with a negative 864 in the numerator. So I have negative 864 divided by x minus 4 squared plus 6, and I need to know when that's equal to 0. I'm going to times everything through by x minus 4 squared, which you can do because, well, because it's going to clear that denominator, and I'm not multiplying by 0 because x is not going to be 4. So the left side becomes 0, and I get negative 864 plus 6. 6 times x minus 4 squared. And I'm going to solve this. I'm going to leave that x minus 4 squared unexpanded, because if you expand it, it's going to be more of a headache than it would be if you don't, because you can just square root here. Divide by 6, 864 divided by 6. 864 divided by 6, let's just do that mentally. That's 144. Okay, we square root so that I get x minus 4 is equal to, well, I could say plus or minus 12, but if it's minus 12 and you add 4, you're going to get a negative, so I don't really need the minus. And we can't have a negative side of a wallboard. I add 4, so x is equal to 12 plus 4, which is 16 inches. Okay. Let's just check we found a maximum. So I'm going to put a 4 here, and x, a prime of x. And I'll put my 16 here. So let's see, let's go up to our derivative. So one version of the derivative that's cleaned up, I'm going to circle. This version of the derivative might be easiest to plug into. For example, let's pick an easy number like 5. If x is 5, you get negative 864 over 1 squared, which is clearly negative 864, which is a negative, so I get a negative. think I misinterpreted. We want the minimum, right? The smallest piece. So we are looking for a minimum. I might have said max. Sorry about that. So my function's decreasing. My area function's decreasing. And then if you plugged in, oh, I don't know. Well, we could plug in, if you plugged in 20 minus 4 is 16. 16 squared is like 256. 864 divided by that is less than 6. So when you add 6, you're going to get a positive. So I have positive, and my function's increasing, so I have a min. Perfect. And so I know one of my dimensions, remember x is still this in my wallboard, the width here, but it wants the dimensions. If it's multiple choice, notice at this point you can cross those off. We just need to find the value of y, and y is up here in terms of x. So okay, so y, notice, was equal to 216 over x minus 4, and x again is 16 now, plus a 6. So that's 216 divided by 12. And this is, so 216 divided by 12 is, let's see, 1, and then there's 9, 96, and 12 goes into 96, 18, plus 6, so it's 24 inches. All right, so it looks like our final answer is 12 inches by 24 inches, which we note is, sorry, not 12. Got all the way there, and then I made put in the wrong value. It's 16 by 24 inches. 16 by 24 inches. And we notice that's letter D. So that one was a little hefty, but all the calculus principles are there.